Hello world, it's Craig. My last video was the ins and outs of Intel hex file format. As promised in that video, this video is going to go over an example 8080 assembly language code to do a transfer, specifically a receive. And as always, this code is down in the description. The code is actually written as a subroutine, so there's a little bit of overhead here that you can ignore for the most part. This receive routine requires no setup other than to tell the user it's time to send the file. It then receives the file over the console input and it saves it to memory using the locations that are in that file. Our entry point for the whole routine is also the re-entry point for each record. So what you see here is going to be repeated for each record since the main outer loop just comes back to this exact same receive Intel hex entry point. First thing we do is I have a white space flush limit value set, and I zero the checksum register. Then the first step is to flush out any input characters until a record mark, the colon, comes along. Basically, this is going to flush out not only any white space before the first record, but it's also flushing any white space between records, carriage return, line fade, comments, anything that's in there between records. And there's a counter on that, so if it doesn't see a record mark within 255 characters, it returns with an error to the user. In this little loop, it checks if the character is a colon, and if not, then the flush limit is decremented and it gets another character. One of two things are going to happen to get us out of this loop. If a colon comes along, then we jump out of this loop, and otherwise we go into the error routine and message the user. Presuming the program eventually gets a colon, indicating the start of a record, the colon is just thrown away and the program now gets the preamble values. This segment gets the number of data bytes and saves that in register B. We then get the addresses. The high byte goes into H and the low byte goes into L, as you might suspect. It gets the record type, saves that in D, and the checksum is saved in C, if you remember we cleared that earlier. So the preamble is done. We have all the information we need. This increment that bumps up the data counter one has just made the looping simpler to include the checksum as part of the data count. We'll look at this routine called getByte in a little bit, but in addition to getting the two ASCII characters and converting them into a data byte, that getByte sub also adds that byte to the checksum value. So the checksum is being taken care of in this getByte. When that code segment is done, the preamble has been retrieved, stored in all the registers. So now starting into this next segment, after the preamble, we know there's going to be at least one more byte in the record. It's either going to be the first data byte. If the record has no data, then it's going to be a checksum. It doesn't matter which it is, we're going to retrieve it anyway and worry about what it is a little later. So we get that byte, decrement the data left counter, and now we know if it was data or if it was a checksum. If the counter is now 0, then that last byte we got was the checksum. That's the last byte of the record. And we can move into the next step of testing the checksum. Otherwise, it was a data byte, so we need to put it into memory, defined by our HL pointer. We increment our data pointer, and we get the next data byte. This segment just loops and loops until all of the data in this record has been retrieved and stored into memory. When we get to the end of this segment, all of the data bytes and the checksum have been received. The data bytes have all been stored. Checksum is still in its register. Now, before we move on to the next segment, the program does a little bit of cleanup and it updates the user. First, it needs to confirm that the record was received correctly, or at least as sure as we can be with such a simple error detection as this single byte checksum method. Since the getByte sub is already added in the checksum byte, the very last byte of that record, that's already added into the running total, so by the time the program gets here, that total should already be 0. Remember, the sum of all of the checksum bytes in this record will total 0. So it's retrieved from its register and tested. If it is indeed 0, then this record passes and the program can continue. If the checksum was not 0, the program loads an error message telling the user there's a checksum error, and it gives the address of the error, and the sub returns to the calling program. And then there's this little step, we back up the memory pointer because the memory pointer has already been incremented, and if we use that, it would send the user looking into the wrong line. So we want to at least set them looking to the right line. This next segment begins, and we know that the record is complete and valid. But only now do I go back and see what type of record it was. And yes, I know what you're going to say, but I'm living in the 70s where the only records were 0 and 1. If a record has any data at all, this program is going to put it into memory at that record address. It can deal with other kinds of records, but if it's got data, it's going to go into the memory. If you live in a world that uses other record types besides 0 that include data, then you'll want to improve on that. So that said, now the program looks at the record type, and with each record type, it cleans things up a little bit differently. In this, the choices are a regular data record, an end-of-file record, or my handy execute record that I talked about in the last video. If it was a data record, it jumps down here where it rewards the user by sending a dot to the console to give them some indication of progress. So as this program goes, at the end of every record, it'll put a dot onto the screen. And then it jumps back to the very top of the routine where it zeroes the checksum, reloads the flush limit, and gets the next record. If that record type was a 01, meaning it's an end of file, then we're completely finished. It sends a success message to the console, and then it clears the carry to indicate success, and then it issues a return. But if the record was anything other than what we know, then it just sets the carry as an error flag, and it returns back to the calling program. So back to what if the record was the execute 0E type that I made up sometime in my youth. The purpose of the 0E type, if you didn't watch the last video, is to transfer execution to some place besides the program that called this. A likely scenario is that we want to download some program, and then right after it's downloaded, when that's complete, we want it to go ahead and run that program. So if this record that the program just processed was this go to an execute type, the 0E, then the program pops the original return address that was on the stack when this retrieve utility was called. And it's replaced with the address that was contained in this record, which is in the HL pair. And then the program continues on as if nothing happened. But whenever this utility is really finished and gets a return, that return we just saw a minute ago, rather than returning to the calling program, it will continue execution at that specified address. And we'll see how this plays out in an example after we finish looking at the program here in a minute. Now note that this execute record type can be anywhere in the hex file, as long as it's before the end of record, that is, or the end of file, that is. It doesn't matter how many of these records are there, the program just winds up replacing the last one with the most recent one in that file. So that's it for the main program. Let's go down and look at that get byte routine. This routine gets the two ASCII characters, converts each to nibbles, and combines them to make that data byte. It also adds that data byte to the running checksum total. The get nibble, in this case, uses the resident monitor's console input and the two hex utilities to actually get the character and do the conversion. 2hex sets the carry if the result is a valid hexadecimal value. And if it isn't, then the two return addresses are popped off the stack and an error message is set up and given to the user. This last segment is the error handler. It outputs the error message and then the current address so the user can find out which line caused the problem. So that's the whole receive routine. If we look at it in the list file, it takes, the length is E8, which is 232 bytes. That's with all the error checking, testing, and messages. So if we forgo all those niceties, then the code takes a little under 70 bytes to actually just complete the transfer. Which isn't all that much considering the value it adds to a resident monitor or a utility package to be able to do these, to receive these files. Now down here at the bottom is another little utility. It's completely unrelated to the receive, but I added it in here just like the stuff at the top that calls that program. And this is a little example that I'm going to use for the execute record type. This routine is located at 2900, and it will send to the console output the string that starts at the address 2920. And then when it returns from that output, it does a warm start. So we'll look at that in a minute. We're actually going to do an execute. So here's the example. I'm running this on my little MCS 85 minimum system. If you like this idea, this little minimum system, there's some videos. They're around 105, I think. There's a few videos on it around the same time I did the SDK 85. It's an 8085, has an 8156 RAM, which also has I/O and a timer, and then an 8755 EEPROM, which also has I/O. And then it has this little 8185 1K RAM. So the thing to note about this is that this chipset was designed to work together with absolutely no glue logic. There's no glue logic necessary on this board. They all decode themselves, including the address latch enable. So what's running in my resident monitor? Let me open up TerraTerm here. These are the commands it knows. It's a pretty basic monitor, but the first thing we're going to do is fill the memory from 2800 to 2BFF. We'll fill that with 00. And this resident monitor already has this download Intel hex file. So let's utilize that to download this program that we just wrote. We're going to tell it to accept a file. Now it's going to go to File, Send File, and get that Receive Intel hex subroutine file. It's going to download this. And it's not your fault I have this at 2400 baud for some reason, so I'm going to speed this up for you. So that's finished. Let's run the program at 2800. So go 2800. So now we're actually running that subroutine we just looked at. Now let's send down that file, and it's just an ASCII file of Gettysburg Address. So let's send that down. We'll also open it up and take a look at it. Here's the Gettysburg Address. It's just Intel hex file. Okay, so receive complete. Now let's do a dump of 2800 to 2BFF. Okay, so this is our program, and you can see that at least half of the program, most of the program is the comments and the error checking and stuff. And then down at the bottom is that Gettysburg Address that this program that we just ran loaded. Now what I'm going to do is go back in and modify that hex file. We know how to do that from the last video, so I'm just going to put in my execute command here. So it's going to start with the colon. It's going to be a 00 because there is no data. And the address of that program was at 2900. And my type to execute is 0E. And now we need to calculate the checksum. So we want that to be in a byte. Let me clear it and add these up. I'm not going to add the zeros, obviously. So 29 plus 0E is 37. Now here's a hint for when you're doing the code that creates the file and you need to calculate this checksum value to tack onto your record. So we can come up with this checksum value in a couple of ways. One is to do the 2's complement, in which case we're just going to do a not and then add 1 to it. That gives us the 2's complement. So the checksum that we want to add on this is C9. The other way, if we go back and we have our 37, what we really want is this to be whatever number it is that makes the sum of all of the other numbers equal to 0. It's the same result as if we just subtract this number from 0. And the easiest way to subtract this number from 0 is to just flip the sign. So if we just flip the sign, then we get C9, which is our checksum value that we need to have. Sometimes in the program, one's a little easier than the other, or it'll save a byte. Complementing and incrementing only takes 2 bytes, but if the accumulator already happens to be 0, then you can just subtract the running total from it and win whatever bet there is by doing it in 1 byte rather than 2. So whatever's easier for you in the program, but in calculator, it's certainly easiest to just flip the sign, which is the same as subtracting it from 0. So let's go ahead and save that and re-download Gettysburg Address. So let's do on this one, we're going to go to 2800. It's now ready for us. This time it's going to download, send the file, same Gettysburg Address with our modification. So this time it's going to send the file. It's going to get to that execute command and save it. And then when it's all done transferring the file, it's going to go back and return to that address. Okay, and here it goes. It did that, receive complete, then it just went to that little routine which printed out that ASCII file. One thing that's kind of handy if you're just testing your code, you don't actually have to send a file. You can just type in a record manually here. So if we go 2800, so I could type in the execute also. That was, no, go 2800. It's a hard way to do it, but it would be a colon 002900 and the checksum was C9, which is going to be 002B5D0177. It's received complete. So I only had 2 records. I only had the execute. So that's the long way around it, but it works. Well, I think that gives you enough so that you can work through this code, you can improve on it, or you can develop your own. That is it for this video, and as always, this channel isn't monetized except for the likes, shares, and other comments that we collect. Talk with you later. Thanks for watching. Bye-bye.